focus point for chemical monitoring and management, which is human activity has caused changes in the composition and structure of the atmosphere. Chemists monitor these changes so that further damage can be limited. So the layers of the atmosphere consist, the major constituents are nitrogen, oxygen, and argon, and the minor ones are carbon dioxide, neon, helium, and okay, so the first layer is the troposphere, which is 0.15 kilometers thick, contains only or mostly nitrogen and oxygen. And as the altitude increases, the temperature gradually decreases. And then there's the stratosphere, which is 15 to 50 kilometers above sea level. And as temperature increases, the altitude increases. And it contains most of the ozone layer, which acts as a shield to prevent UV penetration towards Earth's surface. Then there's the Mesosphere, which is 50 to 90 kilometers above Earth's surface and experiences a rapid decrease in temperature as altitude decreases. And it contains the beginning of the ionosphere and has higher concentrations of lighter gases. Then there is the thermosphere, which is 90 kilometers and above. Rapid increases of temperature as altitude increases, and it's extremely hot due to the molecules being bombarded with UV radiation, solar flares, and other space bodies. And that's just the graph to show where the layers are and the temperatures. The main pollutants in the lower atmosphere is carbon dioxide, which come from incomplete combustion, car engines, bushfires, stovetops, and factories. Oxides of nitrogen from internal combustion and car engines, high temperatures, combustion in power stations, hydrocarbons from solvents and unburnt fuel, sulfur dioxide, smelting with sulfide ores, combustion of fossil fuels with sulfur impurities, lead from leaded and unleaded petrol, paint, electronic devices, old base structures, particulate matter from incinerators, mining, and bushfires. Ozone in the upper and lower. So ozone is an allotrope of oxygen, and in the lower atmosphere it acts as a pollutant, causing respiratory damage, headaches, chronic fatigue, and also a carcinogen. In the upper atmosphere, it acts as a UV radiation shield, so that ozone molecules form a thin layer between 2 to 8 ppm concentration, which absorbs the radiation from the sun, preventing them from penetrating into the Earth's surface. And there are so many typos in here. Okay. Coordinate covalent bonds are formed when one atom contributes both electrons to form the bond. And then there's ozone versus oxygen. So oxygen has a lower boiling point because it has a lower molecular weight, so the dispersion forces are easier to break. It's very low solubility, but ozone is slightly higher because it has a bent shape, so it can dissolve easily in water. The chemical stability is that oxygen is more stable because ozone's coordinate covalent bond allows the third atom to easily break off. Oxidation ability is that oxygen is a weaker oxidant and ozone is a stronger one. Density, approximately the same density as air. Ozone is 1.5 times more density of air. Both are allotropes of oxygen, exist in the atmosphere as gases and contain covalent bonds. Oxygen as a free radical. Normal oxygen has 2 oxygen atoms held together by a double covalent bond. However, an oxygen free radical has 2 electron pairs and 2 unpaired electrons. And there it's closed up directions. Okay, CFCs and halons. CFCs are compounds that contain only carbon, fluorine, and chlorine. Originally designed in 1930s as a gas to be used in the industry as an alternative to other dangerous gases. Used as a refrigerant, solvent, repellent gas, and a building agent. Halons are compounds that contain carbon, bromine, and combinations of hydrogen, fluorine, and iodine. They're used for extinguishing fires, and as their environmental impact became known, they were dramatically reduced. So, okay. The problems with CFCs is that they easily break down ozone, so the CFC photodissociates into a chlorine free radical, and that then reacts with the oxygen, which is with the ozone, breaking it down. And while this is happening, ozone naturally dissociates as well into O2 and oxygen free radical. And because the chlorine is regenerated, it means that one chlorine molecule can destroy up to 500,000 ozone. Okay. Increased incidences of UV-related health conditions is a reversal of CFCs in the atmosphere, because the stratosphere consists of these ozone, and once it gets destroyed, there's a thin layer, and so the UV can enter Earth. With mutation of bacteria and viruses, destruction of phytoplankton resulting in disrupted aquatic food chain, breaking down of bonds and polymers, and immunosphere pressure in humans. Okay, alleviating the problems of CFCs. The Montreal Protocol was made in 1985 to phase out CFC use, and in 2004 they aimed for a 65 reduction by 2010, which they did achieve. Replacement of CFCs with HCFCs, which contain a carbon-hydrogen bond, allowing it to break down more easily in the troposphere. Recently, HCFs were created, and they can't deplete ozone because there's no chlorine. Change in measuring atmospheric ozone. The graph over there just shows that there has been a gradual decrease in ozone concentration over the years. And the three ways of measuring ozone is through UV spectrophometers, so ozones absorb light from a particular wavelength, and this device measures the intensity of the light absorbed and not absorbed, which are then compared, and then calculations are made. Total ozone mapping spectrometer, which are found in satellites orbiting Earth, scan the atmosphere and measure ozone in terms of its geographical position. Helium balloons, which carry UV spectrophometers, providing details based on altitude and location. So one of the questions is to discuss the problems associated with CFCs and assess the suitability of alternative chemicals as a replacement using the data in the table above. Okay. So to answer this 7-mark question, they first stated what CFCs are and the uses of them, and what made them so popular at first, because they did not know the main problem of why CFCs were bad. And then they have the equations as to what CFCs do, which is breaking down the ozone molecules. That's just the explanation of the depletion of ozone. Okay, the next question is explain how this information was obtained, and outline the changes that have occurred in atmospheric ozone concentrations above Antarctica during the past 20 years. Okay, to answer this 4-mark question, you first have to say how this was obtained, which they used UV spectrophometers, and it just explains how they use the light and absorbing and all that. And then kind of explaining the graph of what happens. So talking about how it's more concentrated in some areas and where it isn't. And also that the ozone concentrations above Antarctica are less than other places on Earth due to the polar region's favorable conditions for ozone destroying reactions, which is why there's less ozone above there. Okay, the last question is the graph shows concentration of the CFC known as CFC 11 as measured at the Cape Green Baseline Air Pollution Station in northwestern Tasmania. Explain the concentration of CFC 11 as illustrated in the graph. This is just outlining the trend. So the CFCs were relatively low before, and then they got higher, and then why they got higher, because their use kind of increased and they became more popular. And then can see it kind of decreasing, so that was after the Montreal Protocol that started to decrease slightly. Why is it important to monitor the concentration? You just talk about the effects of CFCs, again depleting the ozone layer and what that does to Earth and health and those problems that were listed earlier in the document. And that is it.